Hi everyone, in this video, we are going to talk about enthalpy. Okay, so please start working on your homework as soon as you finish this video. Okay, so the reading assignment for this chapter section is in the OER textbook, chapter section 8.4. Okay, so we are going to take a look at how to define the enthalpy. Okay, but before we looking at enthalpy, I want to introduce two terms first, so that way you know exactly what we are talking about. Okay, so one is system and the other one is surrounding. Okay, so when we are talking about everything that involved with thermochemistry, you are going to see that there are two different things. Okay, one is system that we focus on, and the other one is everything else, which is considered to be surrounding. So that means in this case, if you define that system would be whatever that we are going to focus on, right? So in this case would be chemical reaction, and the surrounding, as I mentioned, is going to be everything else. Okay, so if I bring this into a picture, it's going to look something like what I'm going to give you in just a few minutes here. But if a system, so this is would be the figure that in what do you call explain the system and the surrounding, right? So system would be what we focus, and surrounding would be everything else. So in this case, if the system gain heat, what happened to the heat of the surrounding? Then if you're looking at this diagram, it would be the opposite, right? So if the heat is going into the system, that means the surrounding is actually going to losing heat, right? So it would be the opposite. So everything, if you add all these two terms together, and that's what we consider to be universe. Okay, so in this context, the universe would be when you add the chemical reaction together, and whatever that surround that chemical reaction would consider to be, or what do you call it? If you add those two terms together, it would be the universe. Okay, so so in this case, if you looking at this, you will see that the heat that lose or gains between surrounding and the system would be the opposite, right? So if the system gain heat, then the surrounding would lose heat, vice versa. But the amount of heat would stay constant, right? Because whether one is gaining or accepting is have to gain and accept at the same amount. Okay. Now let's take a look at more picture of this. Okay, so again, if you have system, everything else would be surrounding. Together, these two considered to be the universe. Okay, so now tie back to the endothermic process that we mentioned in the previous video. Okay, so and also the exothermic process as well, and how we actually demonstrate this in terms of heat flows. Okay, so let's take a look at if you have system. Again, what we are focusing on is what we are studying, right, which is the chemical reaction. So in this case, this system right here is referred to the chemical reaction that we are studying. Okay, so in this case, we care the most about the system. Okay, so in this case, if you're looking at endothermic, what would happen then? We are focusing on system again. So endothermic process is the process that is absorbing heat. So that means the system itself is the one that is absorbing heat. Absorbing from where? Well, it's going to absorb from the surrounding, right? So the Q or the heat symbol that we mentioned in the previous video would be positive, okay? And that is going to be the direction of the heat flow, right? The heat is flowing from the surrounding into the system, okay? So in this case, we say that system gains heat and the surrounding loses heat. Okay, so now the opposite would be exothermic. So the exothermic is the process where the system losing heat. So the heat side would be negative. Okay, so in this case, you can see that the arrow of the direction of heat flow would be going from the system into the surrounding because the system is losing heat. So if you think about this, which one, if you're looking at the endothermic process, which one you think should have a higher temperature then? The answer is obvious, right? It would be the surrounding, right? Because the higher temperature surrounding, that heat is going to flow into a lower temperature, which is the system, right? So in this case, the flow of heat would associate with the temperature difference between the two places. Okay, so same thing with the exothermic as well. In this case, system would have a higher temperature than the surrounding, so that's why it's dispersed that heat from the system to the surrounding. Right. So again, the flow of heat is actually also determined by the difference in temperature as well. Now think about this. What if the two objects have the same temperature then? Well, that's what we call thermal equilibrium, right? So there's no exchange of heat between those two. Okay, so in this case, we're going to focus on the two different processes, which is endothermic and exothermic. One is absorbing heat. The other one is releasing heat. Okay. So that's the summary of these two. Okay, so then let's take a look at an actual chemical reaction here. So I know that this is kind of like easy to see, but now can we actually, like apply that into a real life example? So let's take a look at the explosion of TNT, for example. Okay, so if you're looking at this is the molecule of TNT. Right, so this is the molecule of TNT, and as you see, this TNT here has a lot of bonds. So those energy that store within the bond, those are what we refer as chemical potential. So this is chemical potential, or is the potential energy that's stored within chemical bonds. So as we see that in this case, as the TNT undergo explosion, is produce tons of heat, right? Tons of light, tons of sound, right? So these reaction considered to be exothermic, right? Because it's actually giving up a lot of energy. So in this case, if you see that the what do you call it, transition from TNT to like all these chemicals, right? You probably notice that because TNT give up energy, that means in this case, this TNT is at a higher energy state. So that means this potential energy state here is actually higher than all of these potential energy. Right? So all of these add up together, potential energy would be a little bit lower or at a more stable state. So that's why it's give off a lot of heat or energy, right? Or we can say that this TNT is less stable than of this molecule, right? These molecules are more stable. So I'm just going to tie back into what we learned in the previous lecture video, okay? All right, so now let's get into this, okay? So again, because this is exothermic, so the Q would be a negative. So my expectation for you is you need to be able to assign the sign of heat as well, which is a Q, right? Whether it's positive or negative, okay? So this is going to be a negative because the system is releasing heat, okay? So it's losing heat, okay? So in this case, if you draw this diagram right here, so system is going to, the flow of the heat would going out from the system to the surrounding. Okay, so in this case, system loses heat and surrounding gains heat. Okay, so this is an example of exothermic. All right, so now let's take a look at the word energy versus heat. I know that I kind of like use this term interchangeable, but what do you call, like technically they are not the same. Okay, so and then I'm going to go over why they are not the same. Okay, there is some condition that they are considered to be like interchangeable, but but correctly they are not the same. So I'm gonna actually go over this. So before we get into that, we're gonna define the word internal energy first. Okay, so internal energy is the sum of the kinetic energy and potential energy all together. If you add all of those two together, that is the internal energy of that substance or of that chemicals. Okay. So the second thing that before we do this, I want to mention about the state function. Okay, so these two terms, okay, so the internal energy, kinetic energy, and potential energy. So these are, the internal energy is the state function. Okay, what is a state function? Okay, so let's take a look at that. Okay, state function is something that doesn't depend on path. What do I mean by that? Okay, so let's take a look at this. Okay, so I'm giving you an example of this mountain right here. So let's say that if you are walking using path A and then path B, right, from the bottom to top of the mountain. Okay, so path A would take about 12 miles, right? Path B take about 5 miles. But if you're looking at the elevation, doesn't matter regardless of what path you are taking, the elevation from the bottom to top is still going to be the same, right? So in this case, we can say that in this case, we can say that the route that we are taking is not a state function, right? Because it depends on path, right? If you are take a shorter path, it's going to be shorter, right, than a longer one. So it doesn't, it depends on pathway. Okay. Now, if you are looking at elevation, for example, it doesn't matter which route you are taking, the elevation will still going to be the same, 10,000 feet in this case, right? So that means in this case, the elevation would be an example of the state function. Okay, so the state function, again, does not depend on path taken. So in this case, it's depend on only the initial and the final state. For example, in this case, the elevation here is depend on final and initial state, right? So the final state versus initial state. Okay. All right. So now when we are looking at internal energy. Okay, so we therefore going to looking at the change of or the difference of the internal energy between the reactant and the product, because again we are talking about the chemical reaction, right? Chemical reaction involved with reactant becoming product. So the difference in energy between the product and the reactant, that is going to be the change of the internal energy. But again, remember, it has to be final state minus initial state. So that's why I'm using product minus reactant here. Okay, so we don't care how the reactant convert to product. We care only what are their energy difference between the two. Okay, we don't care whether it's going to take 1 step, 2 step, or 3 step in order to convert from reactant to product. We just care about the final product and the initial state of those two. Okay, so now let's take a look at how is this going to tie back into everything that we learned. Okay, so again, we are going to look at the internal energy change, which is the delta E change right here, which is the difference between product and reactant. Okay, so now we take a look at if the energy of the product is higher than the energy of the reactant. Okay, so think about this. If energy of the product is higher than the energy of the reactant, what is the size of the change in energy? Oh, think about this. Okay, so if this energy is big, right? So if this has a big energy and then the reactant is a small energy, what should be the size of that? So big number minus small number, the answer would be positive, right? It would be positive. Okay, now B, is the energy being transferred to or from the system? Well, remember, positive Q is what? System absorbing heat, right? So same thing here, positive E, the system is actually absorbing energy. So in this case, energy is transferred into system because the system is absorbing that. So therefore, the surrounding is going to lose energy. Okay, so it would be, remember the system and surrounding are the opposite. Okay, so now in this case, we can conclude that energy transfer to the system from the surrounding, or vice versa, energy transfer from the surrounding into the system, right? You can say either way. Okay, now let's take a look at scenario number 4. Okay, so what if you have the reactant that has higher energy than the product? Okay, so if this is big and this is small, a smaller value minus a big value, you are going to end up with what? A negative value, right? So this is when you will see that the energy is being transferred out of the system, right? So the system is losing the energy to the surrounding, right? So in this case, so there would be a 2 scenario between endothermic and exothermic that we talked about earlier. Okay, so now why is this important? Okay, so this is gonna tie back into what we talked about, their potential energy in Chem 1 in the previous video, right? So everything has stored energy, potential energy, and also kinetics energy, which are the vibration, like rotation and translation and things like that. Those random motion that associate with them. If you add all those up together, that is considered to be the energy of product and energy of the reactant. The difference between those two, that is the internal energy. Okay, so now I'm gonna tie this back. Why energy is not exactly identical to heat? The reason for that is because this change of internal energy is actually equal to heat plus work. Okay, so the energy is equal to heat plus work. Okay, for example, if you are looking at a combustion reaction, okay, so let's say of octane, for example, right? So the octane is your reactant, and after it's combust, it's become carbon dioxide and water, for example. So in this case, the difference in potential energy of those octane molecule, right, which is the reactant, right, and then the energy of the water molecule and carbon dioxide molecule, the difference of those two together, that is what we call the internal energy here, and that is equal to heat and work. What does it mean exactly? Well, it means that so again, so Q is heat, right? So I'm gonna go over this side real quick before I get into each of those. Okay, so again, so positive Q, positive heat and positive change of internal energy, those are indicate that the system gains like heat and also gains energy as well, right? So it's depending on what you're looking at. If you were looking at energy, it's gaining energy, right? So if you look at heat, it's gonna be heat would flow in into the system, right? Vice versa with the negative. Okay, so now what does it mean? Okay, so I want you to think about again the combustion of octane in the car engine, right? So in order for car to move forward, right, it's require energy. So this is what the energy coming from. Okay, so once the octane combust, is produce energy, and that's the energy that's the energy that we are talking about here, right? So once octane combust is produce this energy, some of them is going to go toward work, okay, which is this W right here. This W is work. Work is going to be what causing the car moving forward, right? So that's why you are able to move the car forward, okay? But where are the other part of energy going then? Well, that is going to be part of the heat lost that is going to associate with that. So that's why when you drive a car, right, you will feel that the car engine is become really hot, because that is part of the heat lost from this whole equation here, right? So the energy produced from the combustion and the heat is being lost, and some of that is converted into work that moving the car forward. Okay, so that's what it means here. So that means W right here is actually stand for work. Okay, work is going to be something that can be done or on the system or done by the system. So work can be positive or negative as well. I'm not going to talk about much of this, but I just want to introduce that to you real quick, because if you want to know more, right, you can take like 200 series, but in this class, I'm not gonna focus much on work. Okay, so what is work exactly? Okay, so so Q, we mentioned Q before. How do you find Q? Is coming from the change or the difference in temperature, right? So we learned this in chapter 8.1. Okay, so Q equal to MC delta T, remember? So this is what we already learned, right? So you can find out amount of heat from doing that, right? From using mass specific capacity and using the temperature change to find out how much heat involved. Okay. Now with work, okay, you can find work by this equation here, that work W is equal to negative P is pressure time change in volume. Why is it change in volume? Okay, so the change in volume coming from the cylinder in the car engine, right? So this change of the volume right here is causing work, right? So I'm not going to talk much about how to calculate this. Okay, I'm just going to talk about the idea of it. Okay, so that means in this case, work coming from negative pressure, because involved with the pressure as well, right? And then the change of the volume. So in this case, we are harnessed that by the the change in volume in the cylinder. Excuse me. All right, so now what we are going to do is I'm going to show you why I'm able to use the word energy and heat interchangeable sometimes. Okay, so let's take a look at this. Okay, so we know that what we are looking at is the flow of heat or the flow of energy between system and the surrounding, right? So I'm going to go ahead, say that the internal energy of the system would be the amount of it would be the same as the surrounding. How much is gained or is lost is going to be the same, right? Whether it's going to be positive or negative, it would be the opposite, right? Because for example, if the system give off 5 kilojoule, it means that the surrounding is going to if the system absorb 5 kilojoule, it just means that the surrounding need to what? Giving off that, right? So that's why this one is have a different what do you call, like, side, because the side tell you how it flow. It's flowing out or it's flowing in, but the amount of these two would be still the same. Okay. All right. So this thing right here, that the amount of energy are the same, stay constant, is what we call the first law of thermodynamics. Okay, this is very, very crucial. This whole theme right here, you need to know this. The first law of thermodynamics state that energy is conserved, which is the same as what you learn in chapter 8.1, right? So chapter 8.1, you learn that energy never be like neither created nor destroyed, right? It's always stay constant. It's the same thing. It's the same meaning here. It's always conserved. It's always conserved. Why? Well, because it can flow from one place to another place, or it can change form from one form to another form, right? So know that energy is conserved. Okay, so I'm going to do some rearrangement here. What I'm doing is I'm going to add both sides with the delta E surrounding. Okay, if I do that, right, this is gonna cancel each other out. So it's gonna leave off with 0, right? On this side, you are going to have delta E system and delta E surrounding together because I want to move everything to one side, right? So this one right here, which is equal to 0, this is why we call it is conserved, is constant, because when there's nothing changed, right? That's why it's equal to 0. It just means that there is no energy change, right? It's just transfer between the two. Okay. All right, so remember, if you add these two together, if you add surrounding and system together, what would you get? You would get what? The universe, right? So that means in this case, what we can conclude is that the change of the energy of the universe will stay constant. Okay, so that's what this take-home message is. The first law of thermodynamics state that energy is conserved, okay, which is identical to the fact that the change of the energy of the universe will always be constant. It will never change. Okay, because it's just flowing from system into the surrounding, vice versa. Okay, so that's what this is coming from. Okay, so this come from that. All right. So this one right here is crucial, and we're gonna carry this on to the next one as well. Okay, so now we're gonna define that thermodynamics. I'm gonna tie back into the energy and heat in just a few minutes too. So let's actually take a look at this first. So what is thermodynamics, Ren? So thermodynamic is the study of energy and its interconversion. Okay, so we're gonna take a look at moles, take a look at stoichiometry, and later on as well. Okay, so the first law of thermodynamics, or you already see, is energy is conserved. There are 3 laws. So in 122, you are going to learn the first law only. In 123, we are going to cover the second law of thermodynamics and also the third laws of thermodynamics as well. Okay. All right, so tie back into the heat and energy again. Okay, so but before that, I want to introduce one more term before we get into that. Okay, so enthalpy or H. Okay, so this is the enthalpy. I'm going to introduce another term, which is enthalpy. Enthalpy has the letter, what do you call it, the symbol H. Okay, enthalpy is H, and the change of it is delta H. Okay, and this enthalpy is equal to energy plus pressure times volume. Okay, so all of these are state function, which mean that they do not depend on path. Doesn't matter how they reach into the final product. It's only matter between the difference of the final and the initial. Okay, so that's what the state function means. So this is the enthalpy. Okay, and then P is pressure, V is volume. Okay, if you want to jot that down. All right, so what are this then? Okay, so we're going to apply the change to it. Okay, so the change, because they are state function, we're going to do the change of enthalpy of the final state minus initial state. So you're going to get the delta H. Same thing with the delta E, and then P and V. You can do only the change of volume, okay, because the pressure is the atmospheric pressure, is stay constant. Okay, so under, again, the keyword is under constant pressure. Okay, so we're going to take a look at this. Okay, so delta E, we already see earlier, right, is equal to Q, which is heat plus work. Okay, so in this case, we say that is heat plus work. Most of the time, the work that produced is involved with the small change of the volume. So that means most of the time, this work right here is very small. Sometimes it's negligible. So that's why sometimes people will use these two interchangeable. But in this case, I'm just gonna list out so that way you understand better. Okay, so the internal energy is coming from heat plus work. Okay, and because work is negative P, right? So this work right here, sorry, this, we know that this work right here is equal to negative P delta V. So therefore, in this case, if you add a negative to both sides, right? If I time this negative, I have this negative, you are going to obtain a negative W is equal to positive P delta V. So therefore, in this case, that's why P delta V is equal to negative work is come from that. Okay. So now, why do I mention that? Okay, so what I'm going to do next is I'm going to rewrite this whole thing together as I'm going to replace delta E with Q plus W, okay? And then I'm going to replace P delta V with negative W. And then if you cancel those two together, you are going to see that the delta H, the Q is equal to the delta H, which in this case, it tells us that the enthalpy of the reaction is the heat of the reaction, right? Because this is heat, this is enthalpy. So therefore, in this case, enthalpy is referred to as heat of the reaction at constant pressure. All right, so again, this is the take-home message right here if you want to highlight. The next thing I would like to look at is going to be how we're going to tie this back into the endothermic and exothermic process again that we learned earlier, right? So that means in this case, when we talk about endothermic, we already know about the sign of Q. So in this case, the sign of delta H would be the same, right? So if endothermic has a positive sign of Q, therefore it's going to be the positive sign of the delta H as well. Okay, it also means that the system absorbs heat. Okay, same thing for the exothermic as well, right? The sign of Q would be negative. Therefore, delta H, which is the heat of reaction, would be a negative as well. Okay, so enthalpy would be negative for exothermic. It also means that system releases heat. Okay, so again, let me recap it again. So at constant pressure, enthalpy of reaction is equal to heat of the reaction, how much heat involved within that reaction. All right, how to assign endothermic versus exothermic reactions. Okay, so I'm gonna give you a real life example of cold pack that I mentioned in the previous lecture video. Okay, so this is cold pack. How does the cold pack reaction work? Okay, so pretty much most of the commercially available cold pack is made from ammonium nitrate. Okay, so you probably notice that you need to break it or pop it, right? So pretty much you have ammonium nitrate salt in that package, and the other package within the same package is actually water. Okay, once water dissolve this ammonium nitrate, the ammonium nitrate then become what do you call aqueous solution. This dissociation of the ammonium salt into ammonium ion and nitrate ion, this process is going to be the endothermic process, because what happened is that this process is going to absorb heat from the surrounding. That's why surrounding, which is your hand, right, feel cold. Okay, so in this case, heat flows from the surrounding into the system. Okay, so this is going to be the endothermic. So therefore, the enthalpy or the heat of reaction in this case is going to be positive. So that means in order to make solid ammonium nitrate to be aqueous in aqueous solution, right? So you need to actually dissolve in water in this case. It's going to absorb heat. Okay, so that's what it means. Vice versa, if you're looking at hot pack, okay, so hot pack come from, like if you react iron with oxygen, so that's why you have to actually shake it, because the iron need to get react with the oxygen in the air, right? So as you shake it, you will start that is getting warmer and warmer. Why you feel it's warmer? Well, because this reaction is an exothermic, because this reaction, as iron react with oxygen, is going to release heat. So therefore, in this case, you as the surrounding feel the heat coming out. So the heat flow from the system into the surrounding. So they would be an example of exothermic. Okay. All right, so now I'm gonna give you a graphical representation. Okay, so let's take a look at all of this in terms of like reactant going to product, right? So similar to what we see here, reactant going to product, right? Reactant going to product. Okay, so I'm gonna do the same thing here. So I'm gonna plot graph of the endothermic and exothermic. Okay, so what I'm going to do is the x-axis would be the reaction progress. Okay, so we're going to go from, again, reactant to the product, right? And the y-axis would be the heat of reaction enthalpy. Okay, so for endothermic, as we see that the heat is flowing from what? System into the surrounding, or the surrounding into the system. The answer is, yep, so the answer would be the heat would flow from the surrounding into the system, right? Because the system absorbs heat. So the easiest way to remember this, looking at only the system, right? system absorb heat, system release heat, right? So this is absorb, this is release. Okay. The system absorb heat, that means that the enthalpy of the reactant have to be lower than the product, right? In order for this to go up high, it need to absorb that heat. And this is the change, right? That's what I talked about earlier. We care only about the change of the two states. The change or the difference between these two states, that's what we call the change of enthalpy or delta H, right? So in this case, this change right here come out would be positive because again, you are doing product minus reactant, right? If product has a higher value than the reactant, of course, going to come out to be a positive value, right? So this is going to be a graphical representative of the endothermic process. Vice versa for the exothermic would be the opposite, right? So again, so this would be what I mentioned earlier. For the exothermic process would be you have a higher energy of the reactant, and in order for that to go to the product, it needs to release heat, and it's going to be that amount of heat between the difference between the product and the reactant, right? So again, this come out to be a negative because you are using the lower number minus a higher number, you're going to get a negative value. Right? Okay, so example of this would be cold pack and hand pack that I mentioned earlier. Okay. All right, let's take a look at the next one. Okay, so I would like you to take a few minutes here to answer these questions. Okay, and then resume the video again when you finish. Okay, so to check your answer. All right, let's check your answer together. So we are going to determine whether the following process are exothermic or endothermic. Okay, so let's take a look at the first one. When two chemicals mix, their temperature rises. Oh, so that means the temperature rises. So it's going to be exothermic, right? Because in temperature increase, it means it's releasing heat. Okay. Solid burns brightly and releases heat, light, and sound. That's obviously is releasing heat. So it's going to be exothermic. Okay. So just so you know that heat plus light plus sound, all of this together, that's what we, this is called energy, right? Because heat would be the thermal energy part of the energy, right? So light would be, like the energy of light, and sound would be like sound energy. When two chemicals are mixed, their temperature drops. So that would be an example of endothermic. Okay. Two chemicals will only react if you heat them continuously. Remember, like this, the system is continuously require heat, right? Because you need to heat it. So this would be an example of endothermic. Okay, I hope that's give you an idea of what is exothermic and what is endothermic. On the exam, it's going to be similar. You are going to be given a certain scenario and you have to determine whether they are endothermic or exothermic. Okay. All right, the next thing we're going to take a look at is we are going to take a look at how enthalpy or the heat of energy, the heat of reaction involved with the amount of substance. Okay, so think about this before we do anything else. I want you to think about if you have one glass of water that's require 10 kilojoule to heat, for example. Okay, I just make up this number. Okay, so if I ask you, what about if I have 2 glasses of water? If I want to heat these 2 glasses of water up, like how much heat do you need to input? The answer would be 20, right? So 20 kilojoule, because as you double the amount, you are going to have to double amount of heat as well to raise its temperature, right? So in this case, you will see that the amount of the substance affect the enthalpy, okay, affect the heat of reaction. Okay, so why is that important? Okay, so that is going to tie back into stoichiometry. Okay, so the stoichiometry is involved with the amount of the substance, right? So given that, if you are going to produce C and 2D, so this is just the generic equation. Okay, so it's required 2A and plus 3B. And the heat involved with this is 100 kilojoule. Tell me, is this endothermic or exothermic? This is endothermic, right? So it's 100 kilojoule is positive. So this number is positive. So this is endothermic. Okay, so and you probably notice that the reason why I'm blank for a second here. The meaning of this would be in order for A to A and plus 3B to convert to C and 2D, it's going to require this amount of heat. That's what it means. These two need to absorb 100 kilojoule in order to convert to C and D. Okay, so this process involving with A and B absorb heat in order to convert to C and D. Okay, so that's what it means. Okay, so now what if I ask you, what if I have 4A, 6B, 2C, and 4D, then what should be the amount of heat that involved with this reaction? The answer would be what? Well, if you're looking at the coefficient, right? What the difference between the top one and the bottom one is, the bottom one is 2 times greater than the top one, right? So you double everything, right? You see those coefficient, you double everything. Therefore, in this case, similar to the glass of water, if you double glass of water, you also need to double amount of heat. So same thing here, right? So that means the amount of heat that involved with this reaction would be 2 times greater. So that means in this case, the system need to absorb heat, right? 2 times from the original equation that we are given. So in this case, it's going to absorb 200 kilojoule. Okay, so that's what it means here. Now, what about if I have this equation instead? What is different then? Well, if you're looking at these two, right? These two are just flipped, right? So you flip it, right? You flip. Now, this is product. Now, this one become reactant, right? So this is reactant. Now it's become product, right? So you just flip that. If going forward require heat, going reverse direction is going to absorb heat, vice versa, right? So it's just the opposite direction. Okay, so the opposite direction would be an exothermic. Okay, so if the forward is endothermic, the reverse process would be exothermic. Okay. Now I'm going to type this. I'm going to use this enthalpy concept and tie it back with the stoichiometry and why it's important. Okay, so let's take a look at ammonia gas react with oxygen. Okay, so react with oxygen gas. And again, as we learned in Chem 121, in nature, oxygen gas is exist as a diatomic molecule, right? So O2. Cool. So these two going to form nitrogen monoxide. Mono is 1, right? So that means in this case, it's going to contain NO gas, okay? And then water vapor, okay? And it said and 906 kilojoule of heat. So it said form, right? It's form 906 kilojoule of heat. So that means in this case, this reaction is exothermic or endothermic. The answer would be exothermic, right? So this reaction is going to be exothermic because it's producing that much heat, okay? So remember, everything in a chemical equation need to be balanced. So if you're looking at this, you need to ask yourself, is it balanced yet? Right? So if it's not, then go ahead, start balancing this equation for me. Okay. So if you do it, again, I'm going to avoid oxygen because oxygen appear on 2 molecules on the same side, right? So I'm going to avoid that. So I'm just going to start with, hydrogen first in this case, right? So we have 3 here, we have 2 here. So the common number is 6, right? So that's why you have 2 and you have 3 here. Okay. And then because you have 2 nitrogen here, therefore, you're going to add 2 nitrogen right here. So now if you count number of oxygen, you already have 2 plus 3 oxygen, that's equal to 5, but you have only 2 here. So in order to make it to 5, I'm just going to add 2.5, right? Because 2.5 times 2 is equal to 5. So you have 5 oxygen. But remember, so everything has to be in a whole number. So that means in this case, all you need to do is multiply everything by 2, right? To make it to be a whole number. Okay, so by everything by 2. So the balanced chemical equation would be this. Okay. All right, this equation is giving off 906 kilojoule of heat. Okay, so that, I'm going to include negative value right here as well to indicate that this is exothermic. Okay. All right, B, asking you about how much heat in kilojoule that is going to be produced when 155 grams of ammonia is completely reacts. Okay, so that means what we have is we have 155 grams of ammonia. Do you remember, if I have grams, what should you do for the first step? What is the significant about grams? Like, where else do I do? If you go back to 121, you will see that every time when we see grams, we have to convert to mole, right? Because if you want to go from one thing to another thing, mole to mole ratio will tell you about that. Okay, so same thing here. In this case, what we see is that this ratio that we see is not grams to grams ratio. These are mole to mole ratio. So that means if you convert grams to mole, you might be able to convert it into what do you call it, heat as well, right? Because this kilojoule right here is kilojoule per 1 mole of reaction. This is considered to be 1 mole of reaction. Okay, so this is 1 mole of reaction. 1 mole of reaction produce this much amount of heat. Okay, so that's what it means. All right. Or if you're looking at this, right, if you have 4 mole of ammonia, you are going to be able to give off this much heat. If you have 5 mole of oxygen, you are going to give off this much of heat. If you have 4 mole of NO, you're going to give off this much, and so on. Okay, so that's what it tells you. So that means we have the connection between mole and amount of energy here. So therefore, in this case, you need to change from grams to mole first. So that means you're going to convert that by using its molar mass. Okay. And then since we have mole of ammonia already, we know that 4 mole of ammonia, right? So this 4 mole right here is going to give off negative 906 kilojoule, right? So therefore, in this case, you are going to get negative 2.06 times 10 to the third, or 2000, about 2000 kilojoule. Okay, so 3 sig fig. Okay, so another way to set this up. Okay, so this is one way to set it up. Okay, you're looking at how many mole of each of these per how much heat is produced, right? So for example, what conversion factor that you can extract from this is that every 4 mole of NH3 is going to give off negative 906 kilojoule of heat, and so on for oxygen, right? Or you can, it's depend, and you can flip this as well, depend on what unit you want to cancel. Same thing if I want to look at water, right? So 6 mole of water going to involve with negative 906 kilojoule, right? So that's the relationship between enthalpy of reaction and the equation, balanced chemical equation. Okay, now there's another way to do it as well, which is express the same thing. Okay, so I'm gonna move to the next one. The next one I'm going to show you is the same thing. Okay, so I'm going to set up pretty much the same thing that we set up earlier. You have 155 grams of ammonia. Okay, I'm going to again do the same thing that we did earlier, convert that to mole, right, which is 17.03, what is it, 0.3 gram, sorry, 0.7 grams per 1 mole of ammonia. Okay, what I'm going to do is I'm going to consider a mole of reaction instead. Okay, so know that this is also equal to negative 906 kilojoule per mole of reaction. Okay, this unit here, sometimes you are going to see it written as kilojoule per mole, and that kilojoule per mole is actually come from the word kilojoule per mole of reaction. Remember, this whole thing considered to be 1 mole of reaction, right? So that means in this case, I can say that, hey, this 1 mole of reaction is contained or is required 4 mole of NH3, right, of ammonia, right? Because as you see here, right, this 1 mole of reaction is required 4 mole of ammonia. So that's the conversion factor that I can get out of from here as well. Okay, and we know that 1 mole of reaction going to produce negative 906 kilojoule. Okay, if you set up this way, you are going to get the answer identical to the previous one, which is negative 2.06 times 10 to the third kilojoule. Okay, so it's going to be the same. And you probably notice that pretty much what we do here, these two, the difference between that is because you are combining this with 1 mole of reaction together, right? But if you combine that, you're going to get negative 906 kilojoule over 4 mole, which is the same as the previous step that I showed you. Okay, so there are 2 ways to do it. It depends on how you understand it best. So just make sure that you stick with one. Okay, so you can stick with this one, or you can stick with the other one I mentioned. All right, so that's pretty much it for this chapter section. So this chapter section, we are going to tie stoichiometry with what we learned in 121 back, type it together with what do you call it, heat or enthalpy of reaction, right? So this is part of 122. So pretty much it's gonna fall into this mode conversion right here, right? So it's gonna fall into this part of the Chem 121. So if you're looking at this, this part right here, let me tie that back into 121 real quick. This part right here is what we learned from 121, okay? And then 122, this is the part that we actually add to it. Okay, so we use mole to convert to joule using the balanced chemical equation. Okay. All right. So the next thing we are going to take a look at is the standard enthalpy change. Okay. Standard enthalpy change has the symbol of, because we have change, right? So it would be delta, enthalpy is H, and then the standard is the naught sign here. So whenever that you see the naught sign, know that this enthalpy change is at standard state. This naught sign is again referred as a standard state. What is a standard state? Okay, so a standard state is a commonly accepted set of conditions used as a reference point for determination of the properties under different conditions. Okay, so why do we need that? Okay, so here, so in this case, I'm going to use a scenario of elevation again. Why do we need a standard state? So if we take a look at elevation, the standard state of elevation would be sea level, right? So at sea level, because we set sea level at 0, anything above that would be that elevation, right? Like whatever altitude that is, right? So same thing here, the enthalpy, you cannot determine the absolute value. You have to get the relative value, and that relative value coming from what is the baseline that you set it at, right? So it's the reference point, right? So in this case, for the elevation, the reference point would be the sea level. So for the enthalpy of reaction, the reference point would be the standard state condition. Okay, so at this condition would contain pressure of 1 atm and the temperature at 25 degrees Celsius. Okay, and we are going to use this as the reference point. Anything above that or below that would be the actual value that you're going to get as a delta H of the of that substance or of that process. Okay, so I'm going to talk about this more in detail when we talk about chapter 8.7. Okay, so it's toward the end of this chapter 8. Okay, so what I want to talk about first is the standard enthalpy of combustion, which is what we know is the heat of the reaction involved with the combustion reaction. Okay, so what does it mean exactly? So this standard enthalpy of combustion is the enthalpy change when 1 mole of a substance burns. Okay, under standard state condition. Okay, so this is also called heat of combustion. Okay, so what do I mean by that? Okay, so for example, if you have ethanol, okay, so this is the ethanol molecule. If it's combust with oxygen, right, it's going to produce carbon dioxide and water. The amount of heat, if you have 1 mole of this, okay, if you combust 1 mole of this together with oxygen and everything else, right, if you combust that, the amount of heat that involved with this, that at the standard state is going to be the standard enthalpy of combustion, and it's come out to be this value right here for this reaction. How do you get this value? Chapter 8.7 will walk you over that. Okay, so I'm not going to talk about how to get this value, but right now I'm going to use this value instead. Okay, I'm not going to talk about how to get it, but I'm going to talk about how to use it. Okay, so chapter 8.7 will walk you through how to get the edge of the combustion. Okay, so just know that there is the standard condition to use as a reference point to get a certain value that you obtain from the table and things that you see from the table and things like that. Okay, so this reaction is exothermic or endothermic. The answer of this would be what? Exothermic, right? Because it's a negative value. So again, so in this case, I'm just gonna balance equation for you first, and then this is the exothermic process. Okay, so again, remember this is per 1 mole of ethanol, because according to this definition, the enthalpy of combustion, or delta H subscript C here, is per 1 mole of the substance burned. So that's why I need to keep this as 1 mole right here. Okay. All right, so let's take a look at next. Okay, so now I'm going to calculate the amount of heat that associated with combusting 10 milliliter of ethanol. Okay, so if you have 10 ml of ethanol, okay, so how much heat that will be produced if you're burning this? Okay, so we have milliliter. This is the unit of volume, right? So we have volume. Okay, so if you go back to the stoichiometry roadmap, there is no volume conversion, right? Start with grams and mole and things like that. So that means in this case, you need to convert this back into grams first in order to go into grams to mole, right? So in this case, how can we do that? Okay, you probably notice that there is one value that allows you to convert from volume to grams, which is density. Okay, so in this case, what you're going to do is you are going to convert ethanol volume into grams using its density. Now grams, remember, we always convert to mole. So in this case, you are going to convert to mole of ethanol by using its molar mass, add them all together, right? So this is the molar mass of ethanol. Okay. Now remember that 1 mole of ethanol, right? This is 1 mole of ethanol is going to produce this much kilojoule. So we can do that, right? So we know that 1 mole of ethanol produces that much kilojoule. Therefore, in this case, it's going to come out to equal to negative 234 kilojoules. Okay, so again, this is an example to demonstrate that you can calculate for heat involved with the reaction of any chemical that you can combust, right? If you have the list of the standard enthalpy of combustion for each of those substances. Okay. So the amount of heat that you see here, right? So this number might not mean anything to you. So what I'm going to do is that I'm going to actually create the lecture demo for this, so that way you see exactly when I talk about 234 kilojoule, what does it mean, right? So you can actually see it. Okay. So let's take a look at next. You can also use this heat to calculate amount of substance as well. For example, in this case, if it's giving you 200, 35 kilojoule of heat, right? So how can we know that how many pounds of carbon dioxide can be produced? You can do that as well. So you are going to use 235 kilojoule, right? Convert that into mole, right? So in this case, we know that every 1,368 kilojoule is going to require 1 mole of ethanol. And we know that every 1 mole of ethanol is going to produce 2 mole of carbon dioxide. Remember, this mole right here is actually mole per mole reaction. You can say that every 1 mole of, every 1 mole of, so instead of having ethanol here, you can say that it's the reaction as well, right? So 1 mole of, and then we know that 1 mole of reaction is equal to 2 mole of carbon dioxide. Either way, you can use either ethanol, or you can use reaction. Either way is fine, because it's still per 1 mole of that ethanol or per 1 mole of reaction, right? So in this case, if you do that, you will see that you are going to get mole so far, right, of carbon dioxide. And then what you need to do next is convert mole to grams, right, by adding all carbon and oxygen together to get molar mass. And then the last step would be convert from grams to pound, right? So which is going to be 453.59 grams per 1 pound. Okay, so if you do this, you are going to get, let me recheck my calculation one more time, since I changed that. Oh, actually my calculation, this one is already based off the correct number. So this is the correct answer. All right, so again, you are going to see the amount of heat that is being given off from my lecture demo, okay? And then also this lecture demo will also tell you as well that the amount of carbon dioxide that is being emitted, it would be 0.033 pound. Okay. All right, so here are more example for you to practice. And as you see here, right, so this is the kilo 2 per mole is per mole of reaction, right? So you can treat it as mole of one reaction, and one reaction contain what? One, it contain one octane, like that's 12.5 oxygen, right? And so on. So note that this is per one reaction. This whole thing right here is already per one reaction. So that means you don't need to multiply anything else to leave this as it is. Okay, because remember the delta HC is per 1 mole of the fuel, right? So that means in this case it's already 1 mole of the fuel. So that's why I'm not multiplying everything by 2. Okay, so in this case it's okay to leave this as a decimal form. Okay. All right, so you can practice this and find the answer on Moodle. Okay, so please complete your work first before you check answer with the key. Okay, so I want you to actually use this as the exam practice problem. Okay, so use it and see how well you actually understand the material. Okay, and this is everything that we cover for this chapter 8.4. After you finish this, you should start working on homework 8.4 as soon as possible. If you have any question, again, please visit me during office hour.